Hello everybody. Today we shall discuss about the continuous distributions. Generally, we had a definition that if the spectrum of a random variable is a continuous set, or particularly mathematically speaking, if it is a dense set, then we used to call that random variable as a continuous random variable. Now we are going to get a new equivalent definition of a continuous distribution in terms of the distribution function. What is this definition? It says that this is the definition. It says that if the distribution function of a random variable x is a continuous function, distribution function should be continuous, and if its derivative f dash x, this derivative is piecewise continuous. That means f dash x may have some discontinuity, but piecewise means within certain finite interval. Okay, within certain finite interval, the function may have at most finite number of point of discontinuity. This kind of functions are called piecewise function. At these points of discontinuity, the function f dash, this function f dash may be discontinuous. Okay, but otherwise, if we do not consider these points, and through these points, if we divide this interval into finite number of subintervals, then within each and every such subinterval, the function f dash should be continuous. This kind of functions are called piecewise continuous function. Got it? So if the distribution function of a random variable is a continuous function and its derivative is a piecewise continuous function, then that kind of distribution is called continuous distribution. Hmm. Now let's try to find out some features of continuous distribution. Yeah, one of the important feature is that the function f is continuous, and we had a property that the function f is a monotone non-decreasing function, continuous on the right, but over here the function is continuous on the left as well, and therefore the left limit at any point, the left limit of the function f at any point small a, that left limit must be is equal to value of the function at that particular point. And we know that this is a known result, that probability that x is equal to a, this probability is equal to this expression f of a minus f of a minus 0. I proved this result in our previous lectures. And as because this left derivative hmm, becomes is equal to the value of this function, so we can prove that this probability of the event that x is equal to a, this probability of the event of x is equal to a due to this kind of inequality, the probability of the event that x is equal to a ultimately becomes is equal to 0. Therefore, probability of a single point x is equal to a, this kind of event, is always equal to 0 for a continuous distribution. This is very important property. So in case of continuous distribution, this kind of event x is equal to a, this kind of events are equivalent to the null event or the impossible event, because they are stochastically or in terms of probability, their probability is actually 0. So this x is equal to a, the probability that x represents the single value small a is equivalent to the impossible event. All right. Now in this kind of distributions, we get a new kind of function that is called probability density function. In case of discrete distribution, I introduced probability mass function, and equivalent to probability mass function in case of continuous distribution, we have one more function that is called probability density function. Okay. What is probability density function? The probability density function of a random variable is actually this expression if dash x. This if dash, the derivative of the distribution function if dash x is called the probability density function of the random variable capital X, and it is generally denoted by f of x, small f of x. And in some cases, if we consider more than one random variables, in that case, in order to denote that this f is actually the density function of x, we represent this kind of notation f of x, but f has a suffix x. Got it? So this x is a suffix, not any value. All right. So f is a suffix, and suppose if we want to find out the value of this function at suppose x is equal to, say x is equal to suppose 2. Okay. In that case, we shall have to write f suffix x of 2. So this expression within bracket represents the value of the random variable, and this expression, which is actually the suffix of the function f, it represents that this function f is actually the density function of the random variable x. Okay, do not ever confuse this suffix x by the notation of partial derivative. Generally, we have a notation of partial derivative that is also denoted by the suffix x or y, something like that. But over here, do not confuse this with the notation of partial derivative. So this x is actually the real number, the real value of x, and this x is actually the notation represented by the fact that the function f is actually the density function of the random variable x. All right. So be very careful about this kind of notation. Hmm. So this is the probability density function and its corresponding notation. Now we have a very important property that is used as the formula, the probability a less than x less than equal to b. This probability is actually f of b minus f of a. F of b minus f of a. And you see, this fb minus fa can be represented as the integral of the derivative f dash x. Okay, so if we integrate this derivative f dash x with respect to x within the lower limit small a and upper limit small b, in that case we will get this difference fb minus f of a. Okay, and that's why over here in this position of f dash x, if we put small f, the density function of x, then you see the in terms of the density function, you observe that we can compute the value of the probability. Got it? So this value of the probability of the event that a less than x less than is equal to b, this probability, this kind of probability of the event, this kind of probability can be computed by the integral from the lower limit a to the upper limit b, integral of the density function f of x dx. And you see, we already have proved this result that the probability that x is equal to a does not have any probability, or it is actually equivalent to the null or impossible event. So we can over here we can include this point a. Even then the expression on the right hand side expression, this kind of integral would remain the same. Okay, so if we include the point a or if we do not include the point b, in whatever be the case, Yeah, even we can consider this kind of integral include the point A but do not include the point B, or it may be that we consider an open interval a less than x less than b, or it may so happen that a less than is equal to x less than is equal to b, whatever be the probability. Ultimately, this right hand side integral, the value of this right hand side integral would not change at all. Okay, because we know that addition or subtraction of a single point for an integral with where the function f is finite, this kind of function is actually Riemann integrable function. Hmm. So in this kind of Riemann integral function, just inclusion or deletion of a single point does not change the value of the integral. That's why without any problem we can add one point over here, or we can delete one point from this integral. In case of continuous distribution only, we get this kind of benefit. Okay. Now in this formula number one, you can consider this kind of formula where this AP minus FA can be represented as a integral from A to B f of x dx. Hmm? And on this integral, if we take the limit a, this lower limit small a tending to minus infinity, Hmm. in that case, what we shall get? We shall get f of minus infinity over in place of f of a. And if we again further replace this b by a function x, by a variable x, then in place of b we can write this f of x. In that case, the integral would be integral from minus infinity to x fx dx. And you see over here, this is actually a definite integral. Therefore, this x can be replaced by any arbitrary variable t. Got it? That's why over here as well, you can consider this x as an arbitrary variable t. Although we use this notation of x as the upper limit and the variable itself, however, we should have to understand that these two quantities, these are actually the variables of the integration, and this x is actually a fixed value. Got it? So we don't write to different notations. We always write it in this fashion, that f of x minus f of infinity. And what is f of infinity? We know that f of not f of infinity, f of minus infinity. What is f of minus infinity? F of minus infinity is equal to 0. That is actually the property of a distribution function. Hmm? Therefore, we can now write this f of x is equal to the integral from minus infinity to small x f of t dt, or f of x dx. Okay, so over here in place of x, you can also consider any arbitrary real variable t. Okay, so these are the properties of a distribution function. And over here you see, I told you that this density function f of x, this density function is actually is equal to the derivative f dash of x. Hmm. Therefore, it is expected that f should be certain kind of integral, that the capital F function, the distribution function, should be certain kind of integral of this density function f. And this is the result. You see, this distribution function f of x has been represented as an integral of the density function. Got it? This distribution function capital F has been represented as the integral of this density function small f of x with the limit from minus infinity to infinity. All right. So these are some properties and the relations of distribution function and density function. Okay, and we know that this function f is a monotone non-decreasing function. Therefore, this derivative f dash is should be greater than is equal to 0. As because f dash is greater than is equal to 0, so f of x should be greater than is equal to 0. All right, and again in this relation number 2, if we take the limit as x tends to infinity. If we take the limit as x tends to infinity, then what we shall have? We shall have this kind of limit from minus infinity to plus infinity, f of x dx. And if we take the limit extending to infinity over here, we shall have f of infinity. What is f of infinity? F of infinity is equal to 1. Hmm. So we have the second result, that integral from minus infinity to infinity f of x and dx. This value is always equal to 1. So this equation number 3 and this equation number 4, these two should be some two restrictions on the density function f, small f. Okay, if you recall the result that in case of discrete distribution we had a similar restriction on the probability mass function. We had a result that fi, this fi greater than is equal to 0. This was one restriction, and second restriction was that summation of fi, summation of fi from I varying from minus infinity to infinity. All right, this summation was equal to 1. Okay, so over here, this equation number 3 and equation number 4, these are actually two similar restrictions, as because the in case of discrete distribution we used this summation, and in case of continuous distribution, in place of this summation we use this kind of integral. That is the difference over here. So these two, equation number 3 and 4, are two similar restrictions as we had restriction in case of probability mass function. Okay, so probability mass function and probability density function, both of these two functions have similar restrictions, and therefore we expect that both of these two functions should follow similar properties as well. Now we are going to define two more definitions, two more idea. One is the idea of this probability differential. Hmm? What is probability differential? The probability differential of a random variable x. The probability differential of a random variable x is the probability that this random variable x lies in an infinitesimally small semi-open interval like this, starting from x to x plus dx. We always use this kind of semi-open interval, open on the left and closed on the right. So if the random variable x lies on this kind of semi-open intervals, in that case, this probability is called the probability differential or probability element. This is also known as probability element, probability differential or probability element of the random variable x. Got, and the corresponding probability differential, this probability differential is also called the probability differential of the corresponding probability distribution. So whatever be the distribution, if you consider distribution of the random variable x, we have the idea of probability differential. And you see over here, if we try to compute the expression of the probability differential, what would be the expression of the probability differential? Probability a less than capital X less than is equal to b, that is actually written as f of b minus f of x. So we shall have this type of result, f of x plus dx minus f of x. And that is actually the differential of the function capital F. Okay, and this differential of the function capital A, this can be represented as this kind of expression f dash x into dx. And what is f dash? F dash is actually the probability density function f of x, and therefore its expression can be represented as f of x into dx. So this idea of probability differential is used in the many advanced studies, especially where the traditional computation becomes much more difficult. We shall apply this technique in some subsequent examples, but not today. In some subsequent lectures, we shall discuss the application of this idea of probability differential. Okay, and one more definition that should be the definition of the curve of density function. This is known as density curve. The curve of density function fx. If we draw the curve of density function, say this is the density function. In that case, this curve is called the density curve. Okay, this curve is called the density curve of the distribution of x, of the density curve of the random variable. Hmm. And from the discussion so far, you see, we can say that the probability distribution can be obtained from the distribution function, and distribution function is closely related with the idea of density function. In fact, density function is the derivative of the distribution function, and distribution function is actually the integral of the density function. So one function can be obtained from the other function. Therefore, sometimes in the study of probability, sometimes we represent the probability distribution of a continuous random variable by the help of density function or by the help of distribution function. Sometimes we just represent the distribution function. Sometimes we represent the density function. So one can be obtained from the other. So, for example, over here, if you consider this kind of function, suppose we are given this kind of function fx, and over here the question says that we need to find out the value of the constant k, so that this function fx becomes a density function. And after computation of the value of k, we need to find out the probability that the random variable lies in between half and 3 by 4. Alright. So this is the this kind of questions are generally selected as an objective questions of or a short questions of 3 marks or 2 marks. So how to find out the value of this function k? Over here you see some printing mistakes are there in this kind of in this file. So I already posted this file in your Google Classroom. So be little careful about this kind of printing mistakes. Okay. So now let's try to find out the value of the constant k. We know that the function density function follows these two properties. F of x should be greater than or equal to 0, and integral from minus infinity to infinity f of x dx should be is equal to 1. Now over here, let's try to apply this second restriction on the function f. Now you see what is the spectrum of the function x, or what is the domain of definition over here. You see, although the variable x is actually a real variable, but when x varies in between -1 and +1, and in between 1 and 2, then only within this range, then only we have some non-zero value of the function. And otherwise, if the function does not lie within these two open intervals, otherwise the value of the function is equal to 0. So we can say that the only non-vanishing contribution that would come from the function fx, that non-vanishing contribution should come only from these two segments of the function. So from 0 to 1, and from 1 to 2, and the function fx becomes is equal to 0 at other points. That's why we firstly concentrate or decompose this integral from -infinity to +infinity. We decompose this integral into this kind of integral. You see, from 0 to 1 is one segment, from 1 to 2 is another segment, and the remaining segment, that means from -infinity to 0 fx dx, on this kind of region the function f should be equal to 0, therefore its contribution should be equal to 0. And even for 2 to infinity on the remaining portion, where x varying from 2 to infinity, the value of the function is also equal to 0, therefore its contribution is actually equal to 0. So within the first segment from 0 to 1, the value of the function is the expression of the function is equal to x. Therefore, in place of f of x, we just put x over here. And in this segment from 1 to 2, in this open interval, from 1 to 2, this value is equal to k minus x. That's why in place of fx, we just put k minus x and perform the integration. And after computation, we find that the value of the constant k becomes is equal to 2. So in this way, we find that the value of the constant k is equal to 2. Okay. Now we observe over here, you see that the function is defined for all the values of x, but mainly for non-zero segments we have this type of result. And over here again one kind of printing mistake is there. You see, in order over here, you observe that the segments of the density function A is defined by 1, and you observe that this real number system can be represented in this way from minus infinity to 0, from 0 to 1 open interval, and from you can include 1 in any one of these intervals 1 to 2, and over here we shall also get this type of interval. However, you see over here I just forgot to include the point 0, the point 1, and the point 2 over here. So don't make this kind of mistakes. Now within this first segment, that means minus infinity to 0, in minus infinity to 0, this should be 0. This should be 0. So in minus infinity to 0, if we integrate the function fx, you see over here, this is suppose the real line, and the real line over here, this is minus infinity, and say this is plus infinity. And suppose this is the point 0, this is the point 1, this is the point 2. So we first consider this kind of position of x. Suppose this is the position of x. So over here minus infinity less than x less than 0. Got it? And within this kind of region, if we want to find out the function f of x, in that case the integral minus infinity to 0. Over here you see the value of the function fx is actually equal to 0. Got it? That's why the total integral becomes is equal to 0. So value of the function of this function capital f of x becomes equal to 0 whenever x varying from minus infinity less than x less than 0. Okay. Now consider that x lies in this zone. That means 0 less than is equal to x. As because we did not consider 0 over here. We did not consider the point 0 over here. That's why I included the point 0 over here. So 0 less than is equal to x less than 1. 0 less than is equal to x less than 1. This kind of within this kind of zone, if we want to integrate the function f of x in order to find out this function capital f of x, if we integrate the function small f of x, in that case you see over here, the integration can be decomposed into two parts. One is the portion from minus infinity to 0, and another is the portion from 0 to x. Why? Because in this zone, the value of this function, of the density function, is equal to 0. So therefore, the contribution coming from this zone should be is equal to 0. However, within this zone, the value of f of x is equal to x. That's why we put f of x is equal to x and perform the integration, and ultimately after performing the integration, we will get the value is equal to x square by 2. Okay. So in this way, we compute the value of fx whenever x lying in between in between 0 to 1. 0 less than x less than is equal to x less than 1. 0 less than x 0 less than is equal to x less than 1. Now in the second in this position, if x lies in this kind of zone, 1 less than is equal to x less than 2. In that case, you see we have to decompose the total region from minus infinity to x. This is the total region from minus infinity to x. This should be the total in range of integration, and that can be decomposed into this kind of portion from minus infinity to 0, and then again from 0 to 1, and then from 1 to up to x. Alright, so three different kind of integrals would appear. So over here you observe that this is the first portion minus infinity to 0, and its contribution should be equal to 0. From 0 to 1, fx is equal to x, so we put x and perform the integration. And in the next segment 1 to x, over here f of x is equal to k minus x, and we know k is equal to 2, so you can directly put k is equal to 2 in the next subsequent step, or after total computation you can also put the value of k is equal to 2. So after the integration I put the value k is equal to 2, and finally we got this type of result. F of x is equal to this type of expression. So in this way you find the value of fx in this segment 1 to 2, and in the last segment, that means when x lies in this zone, then it should be decomposed into four portions. One is the portion from 0 to 1, second one is the portion from 0 to 1 is the portion from minus infinity to 0, second one is the portion from 0 to 1, and then the from integration from 1 to 2, that is the third portion, and the fourth portion should come from 2 to x. Although every time whenever x is greater than 2, ultimately you will see that you will ultimately find f of x is equal to 1, but that has to be shown by computing this integration. We know that f of infinity is equal to 1, and if over here if you take the limit extending to infinity, ultimately you are going to get f of infinity is equal to 1. You will always get this value, this last value is equal to 1. And if you do not get this value 1, then remember you have some problem in the intermediate computation. So this is a validity checking process. Okay, so don't just skip all this integration process. Please perform the integration, and if after performing the integration you get this value is equal to 1, then it is confirmed that your intermediate computations are all correct. Otherwise it is wrong. So now you summarize the total process, that from minus infinity to 1, that 1 less than equal to x less than 1, sorry 0 less than is equal to x less than 1, this should be 0. This should be 0. The first I had some repeating mistake. And then the third segment 1 less than is equal to x less than 2, and in the fourth segment 2 less than is equal to x less than infinity. So in this way we compute the distribution function capital F of x. Okay, and if we want to find out the probability over here, we know that a less than x less than b, that can be written as a b minus f of a. So f of b, what is f of b? Just x is equal, we put x is equal to 3 by 2, and x is equal to 3 by 2 lies in this segment. So from this second segment you can find the value of the f of 3 by 2, and that would be equal to 7 by 8. If you put x is equal to 3 by 3, you will get 7 by 8. And if you put x is equal to half, then half lies in the first segment, in this second segment. So if you put x is equal to half in this second segment, you will get equal to 1 by 8. So ultimately in this way you can find the probability that half less than x less than or is equal to 3. So in this way you can compute the probability. You can also compute the probability directly by the process of integration. You can simply integrate this function half to 3, this range, from half to 3 by 2, this kind of integral, and you can decompose this half to 3 by 2, this kind of integral, from half to 1. This is the first decomposition, the first segment, and then from 1 to 3 by 2. So in the first segment you can put fx is equal to x, and in this second segment you can put fx is equal to 2 minus x or k minus x. Eventually you will be able to get this probability 3 by 4. So that is again another technique of computing the probability. So as per the question you will have to follow the technique. And in this second question we are trying to show you the converse result. That means some function should be given. We need to check whether this function is a distribution function. Alright. In that case, you will have to check whether this function follows the properties of distribution function. You see over here this function f of x. You can check over here. Hmm. You can find the derivative of this function if possible. If the derivative is greater than or equal to 0, then we can say that the function is not a non-decreasing function. Okay. Obviously, over here, f of minus infinity, if you take the limit extending to minus infinity, you see you are going to get f of minus infinity is equal to 0. Similarly, if you take the limit extending to plus infinity in the last segment, you are going to get that f of plus infinity is equal to 1. Hmm? So, if it is if you can show that the derivative of the function is greater than or equal to 0, then it is confirmed that the given function f is a distribution function. I am not going to discuss all these results. I am going to discuss the summary over here. Ultimately, you will get this kind of result that at the point -1, the left derivative and right derivative of the function of the derivative of the function, the left derivative and right derivative of the functions are different. Similarly, at the point +1, the right derivative and left derivative of the functions are different. Therefore, we can say that the function is not differentiable at the point 0 and at the point 1. However, the left derivative and right derivative of the function becomes equal to same at the point 0. This is the right derivative at the point 0 and this is the left derivative at the point 0. These are all these computations that have been shown over here. I am not going to discuss all these detailed computations. And what does it mean? It means that the function a, this function a is differentiable at the point 0, but it is not differentiable at the point -1 and +1. And if you look at the expression of this function fx, except these endpoints -1, this 0 and this +1, except these endpoints, the function is actually in the interior points, the function is actually two different polynomials. So polynomials can always be differentiable. That's why I firstly studied these endpoints -1, 0 and +1, because at the interior points these polynomials are always differentiable, and therefore we can say at the interior points the function is always differentiable. So that's why we consider this kind of endpoints -1, 0 and +. Okay. So now you can summarize the total result. You can simply say that the function f dash x is equal to 0. The function f dash x is equal to 0 in -1 less than x less than minus infinity less than x less than -1. And you see, as because the function is not differentiable, I did not consider the -1 neither in this segment nor in this segment. I intentionally removed the result for x is equal to -1 because the function f is not differentiable at x is equal to -1. So value of f dash x cannot be computed at the point x is equal to -1. That's why I did not ever include I did not write equal to in the first segment nor equal to in this segment. Got it? So x is equal to -1 cannot be written for f dash x. And in the second segment, what was f? In the second segment, f is equal to 1 minus x square by 2. So if you simply differentiate this expression, you are going to get minus x in the second segment. And in the first segment, if you differentiate this expression, you are going to get simply plus x in the third segment. So in the second segment, value of the derivative should be equal to minus x. In the first segment, value of the derivative should be equal to plus x. And in the last segment, value of the derivative should be equal to 0. This is a constant quantity, so its derivative should be equal to 0. So minus x, x and 0 in the second, third and fourth segment. Value of the derivative should be minus x, x and 0. That's why I have written over here minus x, this minus x, x and 0. And you observe over here I have included equality over here. I have included x is equal to 0. Why? Because the function is differentiable at the point x is equal to 0. So I need to include the point x is equal to 0 either in this second segment, otherwise in this third segment. I have included this result in third segment. And if you combine all these results, you will find that when x is negative, the value of the function is equal to minus x. When x is positive, the value of x is equal to function is equal to plus. So what is this? This is nothing but is equal to the derivative f dash. Sorry, this derivative f dash x is equal to modulus of x. Got it? This is equal to modulus of x when x lies in between minus 1 and plus 1. And otherwise, the value of the function is equal to 0. Alright, so we can say that f dash x is equal to 0 otherwise. And so over here, f dash x is actually our the density function f of x. Okay, so what we observe, f of x is actually greater than or is equal to 0. Modulus of x is greater than is equal. So what we observe? We observe that the function f dash is greater than is equal to 0 and therefore f is monotone non-decreasing function. F of minus infinity is equal to 0 and f of plus infinity is equal to 1, and otherwise the function is continuous function and the derivative is piecewise continuous. Why? Because the function is not differentiable at x is equal to minus 1 and at x is equal to plus 1. Okay, so at these 2 points the function is not, the derivative is does not exist, and so we can say that the function f dash is a piecewise continuous function. There was a printing mistake as well. It should be piecewise continuous function. Alright, so in this fashion we can find that the function f is a distribution function and it is a continuous distribution function and its derivative is piecewise continuous distribution function. Therefore, we can say that the this given function f represents the distribution function of certain continuous distribution. And what is the mass, what is the density function of the distribution? Density function is equal to f of x is equal to f dash x, that is equal to modulus of x when minus 1 less than x less than 1, and that is equal to 0 else. To finish this class, I am going to introduce a few continuous distribution. These are some standard theoretical continuous distributions. The first one is called the rectangular or uniform distribution, and the density function is f of x is equal to 1 by b minus a. Just you see, distribution is always represented in case of continuous distribution. A distribution is always represented in terms of the density function and in terms of its spectrum. So over here the spectrum is a less than x less than is equal to b, and f of x is equal to 1 by b minus a and 0 elsewhere. This kind of if a function has this kind of density function, if a random variable has this kind of density function, then we say that the random variable follows a uniform or rectangular distribution. For example, suppose we have a rod. Hmm. This is the density, picture of the density function from uniform for uniform distribution. Over here, we actually have in between 0 and a, and in between b to infinity, the function should be 0, and in between a and b, this value is equal to 1 by b minus a. You can magnify this one. This value should be 1 by b minus a. Got it? So in this way, we get the density function of the uniform distribution, and you can easily check that this would be the distribution function of the uniform or rectangular distribution. Now, for an example, generally, where do we obtain this kind of distribution? Suppose we have a rod, a rod of finite length. Okay, suppose the rod has this kind of length, and you see, rather considering a rod, we consider a large interval from minus infinity to plus infinity. From minus infinity to plus infinity. Now you consider a finite interval that would be equivalent to a rod. Suppose that this is the origin O, and this first end point is situated at a distance A, and this second end point is situated at a distance B. Okay, then this interval would be equivalent to an interval a comma b. Okay, and suppose you consider any point p, this kind of point p, you consider any point p, and and in such a way that the probability that this kind of interval probability lies in this kind of interval. In what would be the coordinate of this point? This point has the coordinate, suppose x, and suppose the probability that a less than x less than is equal to small x, this probability that a capital X lies within this kind of interval, this probability is proportional to the length of this interval. Hmm? That means that should be proportional to x minus a. If this condition is satisfied, then it can be shown that the function that this random variable x would follow the uniform or rectangular distribution. You see, this probability can be written in this way: lambda into x minus a, and we have a restriction that f of infinity is equal to 1. In this way, we can find out the value of lambda is equal to 1 by b minus a. So if you put the value of lambda in the expression of f of x, you will be able to get this kind of distribution function, and this is nothing but the distribution function of the uniform distribution. That's why we say that x is a uniformly distributed random variable, with these two parameters a and b. These are called the parameters of the random parameters of this uniform distribution. So this is an example of uniform distribution. Now, in the second example of continuous distribution, we consider one distribution that is one of the most important distribution in this probability throughout the probability theory. That is called the normal distribution. What is this? Over here, the spectrum of the normal distribution varies from minus infinity to infinity, and it has two parameters. One is the parameter m, that is any real number in between minus infinity to infinity, okay, and another is the parameter sigma. Sigma is always greater than 0. And how to compute the density function? Over here you see the function density function f of x is equal to 1 by root over of twice pi multiplied by this sigma. We do not consider any square root sign on this parameter sigma, okay, and e to the power of x minus m whole square divided by 2 sigma square. This is the exponent, okay, with this negative sign. This is the exponent. E is the Euler's number e, okay, and if we get this kind of density function, then this then we say that x follows the standard f follows the normal distribution with m comma sigma distribution, with m comma sigma parameters, okay, and you can check that f of x is greater than or is equal to 0, and you can also check this result that minus infinity to infinity f of x is equal to 1. We have one more printing mistake. You see, gamma half should be is equal to root over of pi. So some printing mistakes are there in this file. Be a little bit careful about it. Anyway, so in this fashion, you can check that the total integral from minus infinity to infinity is equal to 1, and that thus we obtain the normal distribution. And particularly if m is equal to 0 and sigma is equal to 1, that kind of special particular case of the normal distribution is called the standard normal distribution. Over here you see I have put sigma is equal to 1 over here, and in place of x minus m, I have put m is equal to 0. So we have 2 into 1 square, okay. So this kind of density function appears, and particularly the for standard normal distribution, the density function has a special symbol that is equal to phi of x, and the corresponding distribution function is represented by capital phi of x. These are two specially important distribution. One is the ordinary normal distribution, and particularly this is the standard normal distribution. So these are two distributions. One is the normal distribution, another is the standard normal distribution. That is actually the particular case of normal distribution where m is equal to 0 and sigma is equal to 1. And the density function of the normal distribution, if you draw the density function of the normal distribution, okay, if you draw the density function of the normal distribution, you would observe that this density function would be symmetric about the point M. About the point M, the density function of normal distribution would be symmetric about this kind of point M, this kind of picture. Symmetric about this kind of point M. And what is M and what is sigma, that we shall discuss later on in this sequence of lectures. Sigma and M has some special important features, special important meaning. The next distribution is the Cauchy distribution. The spectrum is minus infinity to plus infinity, and this is the density function of the Cauchy distribution over here. The parameters are lambda and mu, and lambda should be greater than, strictly greater than 0, and mu may be any number in between minus infinity to plus infinity. This is called Cauchy distribution, and this is the distribution function of the Cauchy distribution. You can check that follows the corresponding properties, that minus infinity to plus infinity f of x dx. F of x dx, I'm writing in short, f of x dx, that should be is equal to 1. Hmm? I'm leaving this checking for you. Okay. Next is the gamma distribution. Gamma distribution has the spectrum from 0 to infinity, and this is the density expression of the density function, that e to the power of minus x, x to the power of l minus 1 divided by gamma of l. If you know the expression of gamma function, you see gamma function, this expression of gamma function, that is actually integral from minus infinity to infinity e to the power of minus x into x to the power of l minus 1 dx. This same expression has been taken as the expression of this numerator. Okay, so it is easy to remember. So in this way we define the gamma distribution, and this is called gamma distribution with parameter L. L is a positive real number greater than 0, positive, always positive real number. Okay, and L is called the parameter of the gamma distribution. You can check that minus infinity to infinity fx dx should be is equal to 1 over here. The second next distribution is the beta distribution of first kind. You see, we have the representation of beta function, that integral from 0 to 1 x to the power of l minus 1 into 1 minus x to the power of m minus 1. So this expression is considered over here as the numerator divided by this beta, the total beta function, this beta l comma m. And as because the integration is performed in between 0 to and 1, you see the spectrum is taken as 0 to 1, this range. Okay, so this is the beta function of first kind, and L and M, these are two positive numbers, because we know that this kind of beta function is convergent only when L and M are greater than 0. That's why L and M are taken as positive quantities. This is called beta distribution of first kind with the parameters L and M. And finally, one more distribution that we should consider is the beta distribution of second kind. Beta function has another representation like this: integral from 0 to infinity x to the power of l minus 1 divided by 1 minus x to the power of l minus m. So this total expression divided by this beta function. Okay, this total expression divided by this beta function would generate this kind of expression, and that's why this expression is taken as the density function, this density function of the beta distribution of second kind. And as because the integration is performed in between 0 to infinity, you see over here the spectrum is taken as 0 to infinity. These are some techniques by which we generally remember the spectrum and the corresponding expression of the density function. Okay, so these are some special kind of continuous distributions that today I wanted to introduce with you, and that's all for me today.